Hi. So far, we've mostly spoken about models where we have an input and then we have an output corresponding to that input. For example, we have an image as input and then we have a label corresponding to that image. Is it a dog? Is it a cat? But a lot of data in this world are in the form of sequences, right? So let's go into sequence models, and the modern transformer is a sequence model, and in today's world we kind of convert everything into sequences, including images. So to be able to get there, we need to understand the basic sequence models such as RNNs and LSTMs, and that is what we're going to do now. So let's briefly discuss RNNs, or recurrent neural networks. So we've kind of seen models like this, the vanilla neural network, where we, let's say, have an image of a dog in, and then we, let's say, have the label dog as output, right? So this is a one-to-one model. But then there can be many different sequence models. For example, you might have still a single input such as an image, and then you might want a sequence of outputs such as the caption of an image, because it's a sequence of words. So the input is an image, but then the output is, say, image of a dog eating a bone, right? So this is a single image but many output, many words as output. So single input, multiple output, or a one-to-many mapping. You can also have a sequence model where you have many inputs and a single output. So what kind of a problem would that be? For example, it could be sentiment classification, where you have a sequence of words, I am happy, right? And you want to know the sentiment. Is it a positive sentiment? Is it a negative sentiment? So you have a sequence of input words, but then you only have a single output. And then this is a many-to-one model. You may also have a many-to-many mapping. When would that be? For example, for machine translation, where you have a sequence of words as input, but then you also have a sequence of words as output. You may have a sequence of words as input, let's say in English, and then you have a sequence of words as output, let's say in French or in German, right? So this is a many-to-one mapping, a many-to-many mapping. Now, what if you have, let's say, so you can also have many-to-many in terms of, say, video classification, where you have the different frames of the video as input, and then for each frame you have a single output, right? So now for every frame you have a single output. But when we were doing, let's say, your sequence to sequence in many to many for, let's say, translation from English to French, in this case your output starts after your input has been ingested, and also the size of the output can be different from the size of input, because you may have different number of words in French as output as opposed to English as input. So now let's look at the details of this recurrent neural network. Firstly, why do we call it recurrent? We call it recurrent because the output is then fed back into the same model, and this is why we call it recurrent. And how do we do that? So before we do that, we also want to maybe predict the output, right, of what this recurrent neural network actually represents. So we will see this in detail. Don't get confused right now, just give it a minute. So what we want to do is we want to create this so-called hidden state, and this hidden state is the new state. So the RNN already has some state, right? It has some hidden state, let's say h of t minus 1, and then given the current input at time step t and the hidden state that it already has, the hidden of t minus 1, and then some function with weights w, some function of parameters w, you predict the current hidden state. And then we use this hidden state in the next time step, meaning now let's say we have the next x, let's say this is x1, now we have x2, or this is xt, now we have x of t plus 1, then we would predict the h of t plus 1 as the function with some parameters, with some weights of now ht and x of t plus 1, and this goes on, and we will again look at this in more detail. The interesting bit is the weight remains same, and again more on this later. So the recurrent neural network, we process a sequence of vectors x by applying this recurrence formula at every time step. So h of t is some function which is which depends on some parameters, some learnable parameters w, our weights, over your hidden states in the previous time step and your current input at time t, your x of t. And remember, the same function and the same step, the same parameters are used at every time step. So this is important. And what I mean to say here is, so now this is the details of what the recurrent neural network actually looks like. So you will have many different t's. Let's say you will have x1, x2, x3 all the way to xn. Right? So this is our sequence. Let's say this is our sequence of words, or this is our sequence of anything, right? And now what we will have are also a sequence of these hidden time steps, right? So this is a vector that is a state vector of your recurrent model, and this recurrent model only has one of them, right? So it will always update it, it will overwrite it. But let's say it starts with this t minus 1. So let's say we have h of 0 where it starts with, and then it has h of 1, h of 2, h of 3 and so on all the way to h of n. And what do? We give it, let's say, x of 1. So what is this function? This function f of w will take my h of 0 and x of 1, and what will it give me? It will give me h of 1. And this f of w actually happens to be this function tan h, and tan h over what? Tan h over these two linear mappings of these two weight matrices, right? So you have a weight matrix here and a weight matrix here. This one we will come to it in a bit. So what are these two weight matrices? There is this weight matrix that goes from hidden to hidden, and then there is this weight matrix that goes to x to hidden, right? So let's say you have a vector x, right? You multiply it with your matrix x of h, xh, it gives you some vector, and then you also have, okay, let me rub the above ones here, right, okay, and then you also have another vector which goes from your hidden to hidden. You multiply it with your hidden vector, right, and this is your x vector, and then this gives you some output, and then you simply do a pointwise addition. So you add your this to this, and then your this to this, and so on, so that you finally add your last one to your last one here, and you then do a pointwise tan h on that. You then do a, after adding, you do a tan h over each of them individually, and that gives you your next hidden state, right? So you started with your x, and your model already came with your h x0, let's say x1 and h0. Now based on this input and the hidden state that your model came up that already had, and using these two learned parameters that again your model has, we then we come to your h1, right? And this is what this recurrence relation is all about. Then using your h1 and x2 and using the same two weight matrices that we have, we get your h2. And then finally, once, for example, if it is now a many to one mapping, you have many inputs, you have many words, but you just want one sentiment, positive or negative. So for that, you then finally have this mapping, which then takes you from your last hidden state, because your hidden state is always overwritten, to your final output that you're interested in. Now, this hidden state is also kind of thought of as this thought vector, right? So it is what the machine learning model is actually thinking. It is kind of an encapsulation of your entire previous sequence into that one vector, into that hidden state. And this is one of the drawbacks that we talk about when we talk about the transformer models, the attention mechanism. But more on that later next week. So what does the computation graph looks like? Well, we have these different weights here. So you have your WXH and you have your WHH, and then using these two and that pointwise addition and the tan H on this, we then get your H1, right? So you start, the H1 was already part, and then you did your function between this and this, and then you got your H1. And then you do the same thing again, right? So you do the same function. So you again have your WHH, you have your WXH, you do pointwise, you multiply this with your H1, you multiply this with your X, you then do this pointwise addition of this, and then on top of all this you do a tan H, and that gives you your H2. And then you keep doing this until your final hidden state. And then you have to remember that the weight parameters, your WXH and your WHH, are the same. It's the same copy, right? It's the same in every time step. We only have one copy of this. And so you can also think of it as shared parameters. We can also call it shared weights, shared parameters in all these time steps. And then you can choose to get output at one or many of these time step, and again you only have this one HW, right? The HY, the one that maps your W, so that maps your H to Y. So you have your WHY which maps your H to Y. And this is the same again here also, all the way here, right? So it's the same that maps your HT to YT. So you have only one copy of your WXX, WXH, WHH and WHY. This maps your X2H, your H2H. You use both of them to create your H, and then this H along with this gives your final Y. It's actually quite simple, and we're gonna see this in a lot more detail in a bit. Also, whenever you're predicting Y, you would also calculate the loss when you want to train it, and then you will have sum of all these losses, and then you will back propagate through it, just the way we have done it for a single model. So instead of the model looking simple like earlier, your model will look like this, and this is also called the unrolled form of your recurrent model, right? You can also choose to have, when it's a many to one, you will have just a single Y, and then you will calculate the loss on just that, right? You will also have, let's say, your target, your ground truth Y hat, and you will calculate your loss between your Y and Y hat, and then you will back propagate it throughout here, right? And then this also goes to the weight vector here and here and here and all that, just the way you do your current models. If it's one to many, then you have input coming in only here. So your weight update to your WXH happens only here, but then the other, your loss comes from all of this, and then your WHH gets updated, even here and so on.